For our last part in Chapter 22, we want to continue looking at the nucleotide biosynthesis and look at the production of pyrimidines. The production of pyrimidines is actually, in my opinion, a little easier to learn than the production of purines. It should be kind of logical. We're making a smaller molecule. There's less steps involved, and we really pay more attention to the de novo pathway. Smaller molecule, we can build it from scratch a little bit easier. So as we go through the production of pyrimidines, we want to pay attention to just a couple of important enzymes, but we also want to think about how the pyrimidine biosynthesis is either similar or different from the production of our purines. So let's go ahead and take a look at the de novo synthesis of pyrimidines. Okay? So the first thing I want you to look at is this picture shown here. This, again, is the easiest way to begin learning how we build the nucleotides. So with our pyrimidines, you see that we can produce our molecule, our basic nitrogenous ring structure, from only two other molecules, carbamoyl phosphate and aspartate. With the aspartate, we're pulling that as an amino acid produced either through biosynthesis of aspartate or from broken down amino acids. We're pulling that from our bloodstream pool of amino acids. With carbamoyl phosphate, we are going to create the carbamoyl phosphate in the cytosol. This is going to be a different carbamoyl phosphate than what we've seen in the urea cycle. So I wrote up here at the top from the urea cycle because I wanted you to remember, oh, I've seen this before, but don't let that confuse you. We are not using the same carbamoyl phosphate. So if we're going to build this pyrimidine using aspartate and carbamoyl phosphate, let's make sure we know how we obtain these two molecules first. So aspartate is pulled from the blood pool of amino acids. Carbamoyl phosphate is made in the cytosol by the enzyme carbamoyl phosphate synthetase 2. So we're following this group here. So we're going to take ATP, bicarbonate, and glutamine, combine them all together to produce carbamoyl phosphate. This reaction is activated by PRPP. Remember what PRPP stands for. That's that phosphorylated ribose 5-phosphate molecule that we use to build our nucleotides. So high levels of that says, let's make some nucleotides. So we kick up this enzyme activity and make the carbamoyl phosphate. This enzyme is inhibited by UTP. Again, ultimate product goes back and inhibits the initial reactions. So now that we have our aspartate and our carbamoyl phosphate, we can put those two molecules together using the enzyme aspartate transcarbamylase, abbreviated ATCase. This ATCase is our committed step. It's regulated very intensely. That is one of the really important enzymes for you to know. So notice we then do a little rearrangement to our molecule and we produce this orotate. You should already recognize one difference. We did not start the pyrimidine biosynthesis with a PRPP. We didn't start with the sugar and build on it. We actually have built this nitrogenous base. Now we bring PRPP in and bring our sugar in, producing ultimately an OMP molecule, and then lose a carbon to produce UMP. So we've produced our first nucleotide. Now that we've made the UMP, we then convert UMP to UTP, then change UTP to CTP. So with our purine biosynthesis, we made a common intermediate and then branched to produce our nucleotides. With pyrimidines, we made one of our nucleotides and then changed it to the other nucleotide. So just another comparison you need to make. Regulation of pyrimidine de novo biosynthesis is heavily controlled at the ATCA step by CTP as well as ATP. So the CTP should make a lot of sense to you. CTP here is the product, so CTP will go back and inhibit the ATCAs. If I have product, stop the reactions, don't make more product. But let's dive a little deeper and think about why is ATP going to be a regulator of this step. ATP is not produced because ATP is a purine. But recall, for every A that we put into RNA or DNA, we're going to put, well, I guess I should say every A that we're going to put into DNA, we're going to need a T. And even though we haven't talked about the thymine nucleotide yet, we're going to make the thymine from one of these molecules that we've already made. So we need the ATP levels to mimic our pyrimidine levels. All falls back to that complementary bonding we see in DNA. So while we're looking at it, let's go ahead and think about how do we make our thymine, our TTPs. We also got to make some deoxys. Up until this point, we've made GMP and AMP, and we've understood how we made CTP. We've understood how we made UTP. We've got to have a deoxy version of every single one of those. To create the deoxy version, we take the ribonucleoside diphosphate of each of the nucleotides, and we react those with the enzyme ribonucleotide reductase. So if this were a ADP, we could make a deoxy ADP. Or if this was a deoxy GDP, we could make, if this was a GDP, we could make a deoxy GDP. This ribonucleotide reductase is going to be regulated by levels of deoxy versus the regular ribonucleotide ATP. This is also an enzyme where we see a lot of our chemotherapy treatments are going to be aimed at this enzyme because we see high levels of deoxynucleotides produced in areas that are rapidly dividing, making lots of DNA. To produce our very last nucleotide, we're going to rely on the knowledge that we've already made our DUTP using the pyrimidine pathway we just looked at, as well as the production of deoxy using the ribonucleotide reductase. Once we have DUTP, we can then directly convert that into our deoxy TMP. So we can make this thymine molecule with one enzyme. As we look at the breakdown of pyrimidines, it's actually much simpler than the breakdown of purines. We will release amine groups directly that can be incorporated into the urea cycle for excretion. And all of the other breakdown products in the catabolism of pyrimidines will lead to intermediates within the TCA cycle, so they can then just enter into the normal pathways of carbon metabolism we've followed this trimester. So we don't have a very specific set of enzymes that we really need to look at for our pyrimidine salvage pathways. Just wanted to reiterate with this slide that it is important to remember we need these salvage pathways, very important in the brain. Most of our salvage pathways are going to rely, especially with pyrimidines, on these free bases being able to have the PRPP added to produce our nucleotides. And then for the last slide, just to make sure you can make good comparisons, here's a comparison of your purine biosynthesis and pyrimidine biosynthesis, so you can make sure you understand each of these points.